in this tutorial, I'm going to give you a quick overview of Maya fluids. Okay, so Maya fluids are used to generate realistic looking fluid simulation, and you can create a wide variety of 2D and 3D atmospheric, pyrotechnic, space, and viscous liquid effects. Okay, you can also animate texture to simulate these effects. So there are two types of effects that Maya fluids can generate. One is dynamic fluid effects and also the non-dynamic fluid effects. Dynamic fluid effects behave according to a branch of physics called fluid dynamics. Okay, so Maya simulates using Navier-Stokes fluid dynamic equations at each time step. Okay, you can apply you can texture dynamic fluids. You can apply forces to them and have them collide with geometry or move with the geometry. It affects soft bodies. It also interacts with the particles. Okay, when it comes to a non-dynamic fluid effects, uh, the fluid solver, the non-dynamic fluid effects do not use the fluid solver to simulate the fluid motion. Okay, you use texture to create a feel of dynamic fluid motion by animating them, and you can create a realistic looking effect using non-dynamic fluid effects. Okay, so the main content for fluid dynamics is its container. Okay, a fluid container is the main component of the fluid effect, and actually it's a 2D or 3D rectangular boundary. um, So you can see here, if I go ahead and click on create 3D container, you can see that now we have a 3D container in X, Y, and G space. And likewise, we can create a 2D container. All right. Fluid cannot exist outside this boundary, this 3D boundary or this 2D boundary. If you're simulating open water effects like ocean and pond, then you don't need a container. Okay. So every container is divided into three-dimensional grid, and this unit is called um, uh, each unit of this grid is called a voxel, volumetric pixel. Okay, so you can create an empty container like I did here, or you can also go ahead and create container with emitter, 3D or 2D. Okay, so if your container is too large, you can if it is too large, you can go ahead and activate the Auto-Resize function. We'll talk about this later in this tutorial. If you have Auto-Resize, you can turn it on, and then Maya will change the size of this container um, according to your fluids. Okay, so this is our 3D container. A 2D container is nothing but a 3D container with depth of 1 voxel. Okay, and fluid emitters, you can add fluid emitters to empty containers by going down to fluid effects and then add edit contents emitter option box, and then from there you can select whether you want a omni type or a volume emitter. So I'll just reset the setting and select omni, apply and close, and likewise for this 2D container I'll go ahead and create an emitter. Okay, I'll select it, move it downwards, also this one, and now if you play your simulation, you would see that emitters are now emitting the fluid. So right now we are in wireframe mode, so let's go ahead and press 6 on keyboard to see it in shaded mode. So it's a 3D container, it's a 2D container emitting fluids, rather emitters emitting fluids. Okay, so fluid emitters should be within the bounds of 3D or 2D container. Okay, and this emitter is capable of emitting density, temperature, fuel, and color. Okay, so if we go ahead and select the emitter here, We go to outliner and select fluid emitter 2. Let's open up attribute editor for this. At the top we have regular transform attributes. Below that we have basic emitter attributes. Alright, so the first thing we have here is the emitter type, and the available options are Omni, Surface, Curve and Volume. As you have seen in Maya particles or N particles, Maya classical particles or N particles. This rate percent is the new feature in Maya 2011, and it's a global value that is scale the individual emitter rates for all the emitter grids for all the voxels, and it controls density, temperature, fuel and density. So if I go ahead and crank this down to 10%, you would see that now we have a very little amount of density here in our viewport. Okay, so let's go back and crank that up to 100. Use per particle rates, rate per pp, radius pp, and the cycle emission and minimum and maximum distance. We'll come to this later, but just go ahead and we'll open this fluid attribute section. At the top we have density method. So before we study density method, let's understand what density is. Density represents the geometry of the fluid. Okay, so this is the, let me switch it to, okay, this shape here is the geometry of the fluid, and it's called density. Okay, so you can use that to create dynamic effects as well as non-dynamic effects. Okay, the method available here is, let me replay this. So we have two density methods here. One is the first one is no emission. If it is set to no emission, emitter will not emit the particular property, in this case density or heat or fuel. Okay. The second one is add. It will add values to the voxels. So if there is existing density there, this method will go ahead and add density to the voxel. Replace will replace density to the voxel. Okay, next we have density voxels per second. It sets the average rate at which density values are emitted into the grid voxels per second. Okay, so if you set negative values here for density voxels per second, it's going to remove density from the grid. Next we have density emission map, and we can use these maps to control the fluid emission. We can plug in any file texture or Maya's procedural textures here. So to demonstrate this, I'll go ahead and delete this 3D container, and I'll add a fresh 3D container by going down to fluid effects and create 3D container. Okay, and now I'll add a polygonal plane here. Let's create polygon primitives plane. Now create one plane here. Let's go to the channel editor and increase the subds here. You make sure that this plane is inside of this 3D container. Okay, let's open up Hypershade and we'll add a new material to this plane, say Lambert, and assign this to this plane. Okay, and I'll also go ahead and create a checkerboard pattern, and I'll plug this into the color map of this Lambert. Okay, so open up this texture, place 2D texture node, and set repeat U and V to 1. Okay, now I'll go ahead and select the fluid emitter for this container. Oh, I'm sorry. First, we have to um, make it an emitter. So let's go ahead and select the select your container, select your plane, go to Fluid FX, and then add edit contents, emit from object option box, and select surface. Go ahead and say apply and close. So it will go ahead and create an emitter for you, Fluid Emitter 3 in this case. And for density emission map, I'll drop that checkerboard pattern here, this texture here, into density map. And now if I simulate this, you'll see that only the areas where texture is white on this plane, the fluid is being emitted. Okay, so this is how you control density or heat or fuel using the procedural textures. So let me get rid of this. Next we have is heat method. Okay, so heat voxels per second is sort of temperature here. So temperature causes fields to rise or react. So it sets the average rate at which temperature values are emitted into the grid. So heat voxels per second is controlling the temperature values, and if you set negative values, it will remove heat from the grid. Okay, like uh, like 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 density emission map, you can also assign procedural textures to heat emission map. Next we have fuel. Fuel values are used to ignite a reaction. Okay, so temperature can ignite the fuel to start a reaction, and during that reaction the density and fuel values get smaller until the reaction is complete. Okay, next we have fluid drop off. It sets the drop off values for fluid emission. So if you're using volume emitters, if you're using volume emitter, the drop off specifies how much emission drop off as you move away from the volume axis. Okay, so if you change this to say volume here, let me zoom in on this and let's simulate and crank this drop off up. You see the value is getting the simulation is getting affected here as we move away from the axis. Okay, so this is fluid drop off. And if you are using omni surface or curve emitter, the drop off will be based on the emission point, and then it radiates out from minimum to maximum distance. And right here we have the minimum and maximum distance if you're using omni or curve or surface. Okay, so that's the difference between the drop off for omni emitters and rest of the emitters. Okay, next we have emit fluid colors. So if I check this on, I'll get this warning, or I'll get this message from the Maya that Maya wants me to make my color grid to the color content method to dynamic grid. So we'll come to that. For the moment, just go ahead and set it to dynamic. Just click on set to dynamic, and by default Maya will emit this brown green color. You can change that, say let's say to red, and now this emitter will emit a red fluid. Okay, so you have that option there for fluid color. Next is motion streak. It's also a new feature in Maya 2011. And when this is on, when fluid streaks is on, and you have say fast moving fluid motion, say if you are creating a missile trail or a rocket exhaust, then you can um, turn the motion streak on, so it will make the fluid continuous um, instead of a series of emission stamps. It will be a continuous streak. Okay, so you have that option there, motion streak. Jitter. So when jitter is on, you get control over better anti-aliasing around the edges of emitting volumes. Okay, so that option is there for controlling the anti-aliasing. Next option we have here is under fluid attributes is turbulence. Okay, fluid turbulence, fluid emission turbulence, and we have two options here, two type of turbulence. One is gradient and one is random. If you want smooth turbulence through the space, you select gradient, and if you want random turbulence, you select random. Okay, so let's select that. Let me stop the simulation. Rewind it. All right. So first value is turbulence. It's the intensity of the force. It's the magnitude of the turbulence, and turbulence speed is the rate of change for the rate of change of the turbulence over time. How fast this changes is controlled through the turbulent speed. Turbulent frequency con turbulence frequency is how many repeats of the turbulence function fit inside the bounding volume of the emitter. Okay, so low frequency values create very smooth turbulence, and high frequency values create high turbulence. Okay, all right. So you get turbulence there. Turbulence offset. It is used to translate the turbulence within the volume. You can give it some offset values, and then within this space here, you'll get this turbulence uh, um, turbulence translation here. Okay. Next we have detailed turbulence. Uh, it's a sort of secondary second higher frequency turbulence. Okay, so if you have a very large scale flow here, very large scale simulation going on, then you can use this to create fine features, fine details in your turbulence. Okay, so it's a little bit render intensive, but you have that option there for detailing your large scale simulations. Okay, next we have emission speed attributes, and it is used to um, these controls are used to emit the speed into the fluids, and we'll come back to this emission speed attributes. Next we have volume emitter attributes. If you are having um, emitter as volume, then you can select whether you want to emit from a cubical volume or a spherical volume. You have option for controlling the sweep, controlling the offset of the emitter. Okay, so so it's a net. This is about the fluid emitter. Okay, next we'll go to the content methods. Okay, now if you go ahead and select your container, and under fluid shape we have the heart of our fluid simulation. So first is container properties. The first option is keep voxel square. So when you set this on, the base resolution is on and the resolution fields are off. And resolution is the this defines the resolution of your uh, container in voxels. So this is 10, 10, and 10 voxels in X, Y, and Z direction. Okay, and if you want to see the shape of or the shape of the voxel or the grid of the voxel, just click here on display, and then for boundary draw set it to full. So now you can see that you have 10 voxels, 1 2 3 4 5 6 7 8 9 and 10 voxels, 10 voxels down, 10 voxels across, and 10 voxels in G depth. Okay, so this is our current density, current grid of the voxels. So keep voxels square, it tries to maintain the square voxels for better simulation and rendering result. Okay, this base resolution um, um, when this keep voxel square is on, then you will have access to this base resolution, and it simultaneously sets the XYG resolution for your fluid container. So if I crank this to 20, since keep voxel square is on and I just set it to 20, I'll get double the voxel count here in X, Y, and G direction. Okay. But if it is off, then you have option for accessing the resolution from this parameter here. Okay, and while creating the 3D container or 2D container, you can set that from this option box, the XYG resolution and the XYG size, 1010 each for 3D container and 40 and 40 for 2D container. Okay, so you can make the resolution via resolution 20 here, but now you will not have the square voxels. Okay, next is the size in X, Y, and Z direction. Okay, you can extend the size by going down to fluid effects, extend fluid, and say I want to increase it in 5 units in -x and 5 units in +x. And if you are having a 3D container, then you can extend it in G direction as well. So if you said apply and close, so I'll go ahead and extend my fluid 10 units in X direction. Okay, so this is the size of the container. Let me go ahead and turn off my boundary draw or change it to bottom, the default one. Alrighty, next we have is the boundary X, Y, and in 3D containers case it's boundary G also. Okay, so the boundary attributes control the way the solver treats property values at the boundaries of the fluid container. Okay, so if I set it to say a boundary Y to -y, so now and okay, now if I set boundary y to -y and play my simulation, now you'll notice that this upper side of this container is behaving like an open space. Okay, like as if there is no roof here in this container. If I set it to +y, now this part will behave like a ceiling, but now the liquid will pass through or appears to be passing through this boundary here. Okay, and if I set it to, let me re-simulate it for you. This liquid will go here, it will collide with the roof, it will come down, and then now it will not bounce off this edge, it will continuously move downwards. Okay, and if it is set to wrapping, what will happen is that fluid will pass through this boundary, and that fluid will then reappear from this side. This is the function of wrapping. Okay, so let me simulate again, and I'll press 6 on keyboard to view this container in shaded view. Now see what happens when boundary Y is set to wrapping. See, okay, fluid flowing off one side of the fluid container to enter at the opposite side. Okay, so let me set that to both sides. Use height field will cover it later. Let's scroll down and find content method. Okay, so we have density here, velocity, temperature, and fuel. Density represents the material property of the fluid. It's the geometry of the fluid. Velocity affects the behavior of the dynamic fluids by moving the density values or fuel values, temperature values, color values, affects all. Temperature affects the behavior of a dynamic fluid. and you can control whether you want your fluid to rise or react or fall down. You can control it through the temperature. And as we already studied, fuel combined with density creates a fluid where a reaction can take place. Okay, color is the color of the density. So if you look at the here we have for density, the content method for density is off. If it is off, there will be no simulation for density. Okay, if it is set to static grid, it creates a static grid for the for this density property. Okay, um, these values, when it is set to static grid, these values can be used in dynamic simulation, but they cannot change due to any dynamic simulation. So if I go ahead and play, you see that now it's pretty much this density is confined to pretty much to this area because grid is static. Okay, and we cannot change it due to any dynamic simulation. Okay, next is the dynamic grid, the default one. It creates a grid for the property, and values are affected by the dynamic simulation if it is set to dynamic grid. Okay, if you set it to gradient, it's used to populate the grid. And let me create a blank, empty container, 3D container, and set it density method to gradient. Default is constant, and it sets the value to 1 throughout the fluid. Okay, the value for the density is 1 throughout the fluid, and gradients are great for creating non-dynamic fluid effects because they render more quickly, and no calculations are required for simulation. कोई आया है? Okay, so let's set it to density, or let's turn this off. Next is wireframe display, and for wireframe you can change the particle type to off, nothing will display here, or set to rectangles. Your fluid will be in the shape of the rectangles in wireframe mode, or you can set it to particles. Next is velocity draw, and this option is used to draw the velocity vectors. And you can see here, you can draw the arrowhead. You have that option there to turn these on and off. You can set velocity skip, so you can reduce number of velocity vectors drawn here. If it is getting too dense, you can reduce the velocity draw. You can crank this up, the velocity draw skip. Okay, and the next option here we have is draw length, and the draw length is the length of the velocity vector arrows. Okay, so this is about the display section. Next we'll talk about the dynamic simulation. Okay, now here under dynamic simulation, to simulate fluid using dynamic simulation, make sure that property type is set to grid. Okay, and velocity should you cannot turn off velocity if you want to use the dynamic simulation. So first option here we have gravity, and by default it's positive 9.8. So if you want your fluid to fall, you can set it to a negative value, and now instead of the rising, it will fall down. Okay, so let me go ahead and change it back to 9.8. Okay, next option is viscosity, And viscosity represents the resistance of the fluid to flow. Okay, how thick the fluid is, how thick the material is. So as you crank this up, the viscosity, you'll get this slow moving liquid, slow moving fluid. Okay, friction is, it defines the internal friction used to, used in velocity solving. When this velocity is solved, okay, this friction, this value here is the internal friction used in velocity solving. So if you crank that up, you'll notice that a little bit of viscosity, so you'd be able to see the effect. It's moving now, the fluid is moving slowly. Next option is damp, and it defines the amount the velocity solution is damped towards 0. And if this value is 1, the flow is totally suppressed. Okay. Okay, so you can control the shape of your fluid, you can control the motion, the velocity using these three parameters: the viscosity, friction, and damp. Next we have is the solver, and two types of solvers are available: spring mesh and Navier-Stokes. By default, Navier-Stokes is used. It's good if you are simulating fluids, air, or where the fluid swirls around. Spring mesh is good for where you have up and down or back and forth motion. Okay, like in waves, then you use spring mesh. Okay, Navier-Stokes is the default. Then we have high detail solve, and here we have option for all grid except velocity, velocity only, and all grids. By default is on. If you set it to high all grid except velocity, you can make you can use high detail solve uh, to make fluid simulation appear much more detailed without increasing the resolution of the fluid. Okay, you have that option here. Um, if you set it to all grid except velocity, it pushes around all grids except the velocity. If it is velocity only, then only the velocity values are pushed around, and if it is all grids, then it's going to enhance uh, your density values, and it will give you a more realistic result. All grid options. Okay, this sub-step is introduced in May 2011 again, and it specifies the number of times the solver perform calculations per frame. Okay, the sub-steps are useful for improving the stability of your fluids. Okay, next is solver quality, and increasing the solver quality increases the number of steps used to solve to compute the incompressibility of the fluid flow. Okay, at this value, and it is referred to as Poisson solve, is the most computation intensive part of the solve, so use it carefully. Next we have good interpolator, and from here you can select which interpolation algorithm is used to retrieve values from points within a voxel grid. Default is linear, which is quite fast. You can also set it to Hermite, and a Hermite curve is used. If you use Hermite, then Hermite curve is used to interpolate the fluid. Okay, this method causes less diffusion than linear. Um, if it is recommended that you use Hermite when you want friction to be computed by the solver at the boundaries, then you use Hermite. Okay, next we have forward advection. Forward advection is useful for simulation that have compression effects. Then you turn this on if you are having compression effects in your fluid. Start frame, and start frame is it sets the frame after which the fluid simulation will begin. Okay, default is 1. um, Simulation rate scale scales the time step used in emission and solving. Okay, you can disable evaluation for this solver, nothing will happen if you select it. Okay, conserve mass, use this option when updating the density, and you know when you update the density and want to conserve the mass, then turn this option on. You have collision, use collision. If you want to disable the collision of the geometries with the fluid, you can turn this off. Use emission, you use this option off to turn this option off to ignore all connected fluid emitters during simulation. And use field is used to this option is used to ignore all connected external fields during simulation. Okay, so this is about the dynamic simulation. Next we'll talk about auto-resize. The auto-resize function option automatically dynamically resizes the 2D and 3D fluid containers when voxels near the outer boundaries of the container have positive density. Okay, it's driven by the density values. The smaller the simulation area, um, it will increase the simulation speed and also reduce the render time. It will also use less memory, and if you are creating a cache files, the file size will be smaller. Okay, so let me turn this on, auto resize, and play the simulation. You can see that density values are affecting the size of our container, and it's getting bigger and bigger in X and Y direction. Okay, because it's a 2D container. When this option is on, you'll get this resize close boundaries, and when this is on, fluid container resizes along the axis that have their respective boundary attributes set to either none, um, sorry, container details, either set to none or both side, or positive side or negative side. Okay, so if I set it to say boundary y to minus y, and just close this option off, shut this option off, let's see that now my grid, my container is expanding in the y direction only, not in the x direction. Alright, so let me set that off. Next is resize to emitter. So when this option is on, the fluid container reaches the fluid emitter's position uh, to uh, uh, to set its offset and resolution in the scene. So let me go ahead and animate this emitter. I'll set a key here and around frame 50. I'll move it here and press S. Now if I rewind, you see that the container will resize uh, according to the moves of our um, emitter. Alright, so you have that option there. Next we have, let me undo this. Okay, next option we have under auto resize is the max resolution, and it specifies the average maximum resolution per side that a fluid container resizes when resize to emitter is on. Okay, so for example, if the max resolution is set to 10, if this value is set to 10, then the fluid cannot be greater than of the grid 10, 10, and 10. Okay, so you can have a grid value like 5, 20, 10, so it equals this, but you cannot have like 6, 20, and 20. Uh, okay, so this this is how this max resolution works. Next is dynamic offset. It displays the the local space translation of the fluid that is computed when auto-resize is on. So you can animate this value here to control the dynamic offset. Okay. Next is auto-resize threshold. So when auto-resize is on, resize density threshold sets the density threshold value that causes the fluid container to resize. Okay. So this is directly related to the auto-resize option, auto-resize feature of our container. Okay. So next we'll talk about self-attraction and repulsion. Now let's talk about self-attraction and repulsion. And by default, this value is off. So self-attraction and repulsion depends on container's density or temperature value. As you can see from this drop-down menu, either we can control the attraction and repulsion forces through density or the temperature. So by default it's off, so no self force will be applied to voxel in the fluid container. If you set it to density, the self force to be it sets the self force to be based on the density grid values, and if it is temperature, then sets the self force to be based on temperature grid value. So let's go ahead and set it to density. Now we have self attract. um, it sets the strength of the attractive force, and self-attract does not affect the voxels that have density or temperature value greater than this equilibrium value, and there's sort of these two values are connected with each other: self-attract, self-repel, and equilibrium value. So you can set the self-attract value here, and the equilibrium value here, as you can see. um, Self-repel assess the strength of the repulsive force. Okay, and again it does not affect voxels that have density the density value um, less than this equilibrium value. Okay, and at last we have this the self force distance. um, it sets the maximum distance um, in voxels that the self force is applied. For example, if you set this value to 1, um, voxels are only affected the um, by the self force generated by the voxels next to them. Okay, so this is what a self force distance does, and self force distance value can increase your simulation time. Large self force distance values. Okay, so if you increase the resolution of a fluid container, you should increase the force distance value to obtain the same effect. Okay, so keep that in mind. All right, now let's talk about content details, and first section here is density. Density scale multiplies the density values in the fluid container by this scale value. Okay, so if density value is less than 1, it makes the density appear more transparent, like in this case here. Okay, and a value greater than 1 will make it more opaque, and the default value is 0.5. So if I go ahead and say 1 or 2, you can see there that we have opaque density here. Okay, so let's set back it to 0.5. Buoyancy, if the buoyancy value is positive, the density represents a substance that is lighter than the surrounding medium, and it will rise. If you set it to negative value, say say -1, then the liquid will will fall instead of rising. All right, so let's set back it to 1. Dissipation is it defines the rate at which the density it gradually vanishes in the grid. Sorry, not the buoyancy, but the dissipation. again, as you can see here. Next is diffusion, and it defines the rate at which density spreads into the adjacent voxels. See there. Okay. Next is noise, and it was introduced. The noise, tension, and gradient force. These three parameters were introduced in Maya 2011. And what noise does is this: it randomizes the density value at each simulated step. So you can give your fluid some details and some sort of turbulence using this option. But be aware that high noise values can add unwanted jitter. As you can see here, a little bit of jitter going on there, so use it sparingly. The noise value. Tension is again the new feature, and it pushes density into the rounder shape, and it gives it gives your fluid simulation some detail, you know. Okay. And this effect is similar to, like, you have um, the surface tension in liquid, but this value, the tension value, it does not affect the velocity in the grid. Okay, this is what this tension does. The gradient force is similar to self attraction and repulsion. Positive values um, positive values produces attractive force, while negative values produces a repelling force. Okay, so it produces, the gradient force produces similar effect as the self attraction and repulsion, but the effect is localized to the adjacent voxels, and um, this this is less computational intensive gradient force than self attraction and repulsion. Okay, next we have velocity. We have velocity scale in x, y, and g. It scales the velocity relative to the fluid, and it multiplies the velocity value within the fluid container by this scale value. So if I go ahead and set it to 2 in the y direction, it will boost the velocity in the y direction. Okay, next is swirl, and it defines the amount of swirliness in the velocity solution. Okay, so you'll get these swirls effect. All right, so this is what swirl does. Noise is again new feature of 2011 under velocity, and it applies randomization to the velocity values. Okay, this noise will give you randomness in the density values, while under velocity this noise will produce um, produce randomization in the velocity values. Okay, next we have is turbulence, and this turbulence strength is you increase this value to increase the amount of force applied by the turbulence. Okay, and next we have frequency. If you lower down the frequency, the vortices will be larger. Okay, and if you make the value larger, the vortices will be smaller. So this is how frequency, this turbulence frequency, affect your fluid. Speed defines the rate at which the turbulence pattern changes over time. So you can control that from here. Okay, so strength is the force, the strength of the force. Frequency, it is used to define the vortices inside of fluid, and speed is the rate of change at defines the rate at which the turbulence changes over time. All right. Next we have temperature here, and options are exactly same as we have seen in the density: scale, buoyancy, dissipation, diffusion, noise, density, and tension. I mean noise and tension. So pretty self-explanatory. And as you can see here that the parameters are grayed out because we have to go to content method and set temperature to dynamic grid and also fuel to dynamic grid. Now you would be able to see the options here for temperature. So you can control temperature, scale, buoyancy, dissipation, diffusion, turbulence, noise, and tension. Under fuel, we have fuel scale, and it multiplies the fuel values defined in the container. Reaction speed is how quickly the reaction converts from 1 to 0 when temperature is at or above the max temperature. Okay, this ignition temperature is the lowest temperature at which the reaction will occur. The max temperature is the temperature beyond which a reaction occurs at the fastest speed. Heat release is it defines how much heat is released into the temperature grid by a reaction. Okay, right. Light release is the amount of light released by the reaction. Okay, and it is directly added into the final incandescent settings of the shading that you can find here. Under shading, you have incandescence, so the light released will be added here, so it's very important, this feature. And then the light color, it defines the color of the light. um, it's the color of the light that will be released. Okay, next we have color, and we have two options here. If you are using dynamic grid for color, all right. So for dynamic color, you have two options: color dissipation and color diffusion. This color dissipation defines the rate um, at which the grid dissipates, the color dissipates in a grid, and color diffusion um, defines the rate at which the color diffuses into the adjacent voxels in a dynamic grid. Okay. Next we have grid cache, and you can select from here that which grid cache to be read when playing a dynamic simulation. So you have options for reading density, velocity, temperature, fuel, color, texture, coordinate, and fall off from the cache. Okay. Next section is surface, and we'll cover this in the part 2 of this tutorial.